So today we're going to be talking about inductors in an AC circuit. You see, so if you have an inductor, let's say here is a simple AC circuit. This coil here is known as inductor. And of course, here is the AC source. Here is the ammeter. The voltmeter is connected end to end. Sorry, from both ends of the inductor. You see, so if we have an inductor in an AC circuit, the voltage begins to lead. The voltage leads the current by a quarter of a circle, of a cycle, and that's 90 degrees or pi over 2 radian. Now this is shown clearly in our experiment and also in theory as well. So the voltage, if you have an AC circuit with an inductor inside, just an inductor only, and you connect an oscilloscope to both ends and try to measure, carry out a measurement, you see that the voltage will lead the current by 1/4 cycle, and then the current will also be said to lag the voltage by the same 1/4 cycle, or pi over 2 radians or 90 degrees, the same thing. You see, so the voltage leads the current by a quarter of a cycle, 90 degrees or pi over 2 radian, while the current lags the voltage by the same margin. You see, so if you draw on a graph, plot on a graph, the voltage, the instantaneous voltage with time in an AC circuit, you'd see that it leads the current in this way. If you were to plot the two together, okay, here let's say here's the instantaneous current, here is time. If you plot it against time, you'd see that both of them will be out of phase, that is the voltage and also the current, by what? A quarter of a cycle. And what do we mean by something being out of phase? It means the peaks do not occur at the same time in space. Also their troughs do not occur at the same time in space as well. So while this one is minimum, here is just reaching 0. You see, when this is maximum, here is minimum. When the voltage is maximum, current is 0. When the voltage becomes 0, then the current is maximum. See, it leads the current. You see, like that. So this is what you're going to get in an AC circuit containing an inductor. You see. So, since the voltage leads the current by this margin, it means that if the instantaneous voltage is given as V0 sine omega t, which is the general formula for instantaneous voltage at every point in time, the voltage is given by this. It's time dependent. So if it is given by that, means the corresponding current will be given as I equals I0 sine omega t, which is the phase angle, minus pi over 2 radian. You see, and if we give the current to be I0 sine omega t, it means that the voltage, since it leads the current, is going to be V0 sine omega t plus pi over 2 radian. You see? So now, when we apply Ohm's law, you know, by Ohm's law we say V equals IR, right? But in this case, the R has to be something else, but we'll come to that later. So if you apply Ohm's law to this, in this AC circuit here, V is going to become IXL, where XL is known as inductive reactance. XL is known as inductive reactance, and its SI unit, very much like capacitive reactance, its SI unit is still ohms. Why is it ohms? Because it's basically an opposition to the flow of current, very much like resistor or resistance. So it has the same SI unit as well. Okay. But XL is equal to, which is inductive reactance, experiment shows that is equal to FC. Unlike capacitive reactance, you know, remember capacitive reactance is 1 over 2 pi FL, where L here is the inductance of the inductor, and the SI unit of the inductance of an inductor is Henry, denoted simply by a H. You see, so the L here is called inductive, so the inductance of the inductor, and is given by this, the inductance of the inductor. The SI unit of it is L, which is, the SI unit of it is H, which means Henry. H for short. So if there is a question, you can let me know so I can talk more about this. But before I go on, I would like to explain from the very start. So here we say inductors in an AC circuit. So if you have an AC circuit like this figure here, this coil here is known as an inductor, and it has an inductance, it has a value. The value of it is called the inductance of the inductor. So in an AC circuit, it also performs very much the same function as your resistor, because it opposes the flow of current, very much like a resistor too. So when it does that, we say it's got an inductive reactance. You see, so we say inductive reactance is the opposition to the flow of current. Okay, I didn't write it down here. So the inductive reactance is the opposition to the flow of current offered by an inductor in an AC circuit. You see. So that's how it is. Now, we said in this kind of AC circuit where you have only an inductor, that the voltage leads the current while the current lags the voltage. Of course, by the same 1/4 cycle, a quarter of a cycle. Now, if you draw a cycle divided by 4, the angle there is 90 degrees. And of course, if you were to measure, convert 90 degrees to, to radians, which is the natural definition of an angle, you get pi over 2 radian. See? So if you're to plot the instantaneous voltage in an AC circuit containing an inductor against the current, to get something like this. And then if you do the same thing for instantaneous current in such a a circuit, you're also going to get something like this, where, as you can see, the voltage will lead the current by a quarter of a cycle. You see, the both of them are out of phase, and that means when this one is reaching its peak, this one is not in its peak. You see, and as it happens, when voltage reaches its peak, it will take another quarter of a cycle before current reaches its peak as well. You see, so when you apply Ohm's law, you know, Ohm's law is basically V equals IR, where R here we can replace R by the inductive reactance XL, and then the whole thing will still hold. Of course, the SI unit of inductive reactance is, like I said earlier, ohms, and inductive reactance is given by 2 pi f L, where L is the inductance of the inductor. See, and is measured in Henry. Thank you.